We're ready to start. Tomorrow, as usual, every other week, we'll have a test. The test is, we will let you work for up to 30 minutes for the test. The test doesn't take that much, but we will not force you to leave the room before 30 minutes. We have seen the basics of TCP. We will see now a few examples of one of the many variants and sub-algorithms that exist in TCP. I recall that a bit later, we will also see congestion control, which is a very important part of TCP, but that we don't discuss here. There are many subtle things to do in TCP, partly because of the streaming service, in particular, when to send a packet. Assume, for example, you have an application that does writes into the socket interface by very small amounts. In the worst case, it could be 1 byte at a time. So assume you have a program that does this. Now you are designing the kernel function of TCP, and the question is, what should you do? You have received a large number of writes. What should you do with those very small elements that you have to send? Should you send 1 packet for every byte that is sent, or should you merge them together until you have a packet that is large enough? By default, most implementations of TCP will implement an optimization, which is called Nagel's algorithm, which we will not see in detail, but it's very easy to understand. Nagel's algorithm will try to avoid sending very small packets by waiting a bit and for a very short amount of time until a large packet that is large enough is sent. You can disable Nagel's algorithm if for some reason you want a very reactive application. If your application is truly writing 1 byte at a time and it's important to send that byte as soon as possible, you can disable it. It's one of the many options that exist when you use sockets. The converse of that is on the receiving side, when to send an ACK. If you receive 1 packet with 1 byte each, should you ACK each of those individual packets, or should you wait a bit? So there is a similar things. There are other more funny things like the silly window syndrome avoidance that I will let you discover, but it's a combination of all those things where it can happen that based on how the application reads and the other application at the other end writes, it can happen that the window moves by 1 byte at a time. It's called the silly window, and there are also heuristics to avoid that. So those are easy heuristics that are almost obvious and that are old. What we will discuss today is those 3 heuristics that are here. One of them is how to detect a loss. That seems to be the basic function of TCP, but surprisingly, there are more than 10 different ways of detecting a loss. They have names like fast retransmit, fast FACK, SACK, etc. We will see a few of them. The important thing to recall is that each of those are heuristics, and they are in some sense compatible. You can have a very aggressive TCP on one side that decides to repair losses as soon as it has a hint that maybe a loss occurred. The price to pay would be, what would be the price to pay if you have a very aggressive TCP sender? Pardon me? Would send too many packets and overflow the sender? No, that should not be possible because we have the window flow control of TCP. You're not allowed to send packets that are outside the window. And if the receiver is flooded, it will send you a window advertisement to force a small window. So that will not happen. But what might happen is that you have unnecessary retransmissions. The same packet may be transmitted several times. It is allowed by TCP. There's no way to make it impossible, because you never know whether something is lost because the packet is lost or the ACK was lost. So you may think that a packet is lost when in reality it has been received. So it should be perfectly legitimate for a TCP receiver to receive the same bytes several times. But since all the bytes are numbered, if you receive bytes that have already been received and are already in the socket buffer, you ignore this. It's a repetition. That may happen, and there's no way to totally avoid that. So there's a lot of freedom on how you implement retransmissions and loss detections, and many versions of TCP exist that are more or less aggressive. We will see also two further optimizations that are called SYN cookies and TCP fast open. But let me start with a small question here. Oh, it's not the correct one I put here. Yes, it is. We have seen this diagram already, where we see on the left a TCP sender that has sent two packets that have been lost. The third one was not lost, and then it receives an acknowledgement. The ACK field, I recall here, is always the cumulative value. So the ACK field is the largest number you can ACK contiguously. And if you need to ACK more things, you put them in one or several SACK blocks. Here the ACK field is this value corresponding to the packet at the top, and the packet here at the bottom that was received is acknowledged in this SACK block here. Now you could say, if I receive this, certainly there is a loss, therefore I should retransmit. Is it a good idea? That's the question I'm asking you. And we see that we have an almost even distribution between A, B, C. Well, it is one of those quizzes where there is no good answer. And that's why there are so many different ways of doing retransmissions. Some implementations of TCP do it. So they say, if I receive something like this, then I decide that it is a loss and I retransmit. Some other implementations of TCP are a bit more careful, and they analyze things like, they analyze what are the numbers here, and in a case like this, the number is very high, so there is a large gap. So some heuristics will see if the gap is very large, probably there is a loss. Because what would be the alternative explanation to a loss? Could be a loss of an ACK, but since we have received an acknowledgement here, we still have remember, acknowledgement is always trying to acknowledge everything that I've seen so far. We don't just acknowledge the last thing received. So this acknowledgement gives us the answer. So even if we lose one or two acknowledgements here, this is repaired as soon as we receive a new one. But it could be that there is packet reordering. It could be that those two packets, 3 and 4, are not lost, but they're on their way. They will arrive a bit later. So if you do such a heuristic, you have to make sure, if there is a bit of reordering, that you do not retransmit immediately if the cause might be reordering. There are multiple heuristics that try to do this. We will see immediately one of them, which is one that is implemented in practically all implementations of TCP. It's called fast retransmit. Here the idea is, if I receive a single SACK block with a gap, I do nothing. But if I receive that repeatedly, I will do something. And how much you have to repeat? Well, there is a system constant, which is the max number of duplicate acknowledgements. Here, duplicate acknowledgements is a bit confusing. It's not an acknowledgement that's duplicate, it's the ACK field, which is duplicated. The ACK field, verbatim, is the field in the TCP header that acknowledges everything up to that has been received in sequence. So if, for example, here, the ACK field we see here is the same as this one. So those two packets are considered as duplicate acknowledgements. Again, this is misleading. They are not really duplicate. This one is giving a different information than this one, but the ACK field is duplicate. Right? So the fast retransmit heuristic says if you receive up to, for example, n equal 2, many Windows implementations do 3. I believe other implementations have smaller numbers. Here, if you receive up to n duplicate acknowledgements, you decide that there is a loss and you retransmit. So in this case here, if this packet is lost, we see what happens. So this packet is lost. Packets 1 and 2 are those, the blue packets 1 and 2 are acknowledgements for packets P1 and P2. And I'm showing here only the ACK field. The SACK field is shown in smaller character. We see that when we receive the blue packets 3, 4, 5, we have received the same ACK field 4 times. So we have 3 duplicates. So if n is equal to 3 in your operating system, at the third duplicate, which is the fourth time you receive an acknowledgement field that is the same value, you declare a loss. And this figure is illustrating the underlying assumption that is made here. We assume that there is a stream of data that is being sent, which is the case here. So there are 6 packets that are being sent. If one of them is missing, then we will detect the isolated loss by those duplicate acknowledgements. So this is one heuristic that is very often done. Statistics by Google, for example, on YouTube show that this catches about 50% of the losses. We'll see there are other things you do. And the thing you always do when you're stuck in a distributed system, because there's an impossibility result of some kind, you put a timer. And when the timer expires, you repair the bad things. We've seen that for deadlocks. We've seen systems where deadlocks can occur. An example of deadlock was? Yes, but in this course we have seen a
slow receiver and fast transmitter, so it's waiting for the other to
slow receiver, fast transmitter, and the slow receiver is sending a window of 0. Then the transmitter is blocked until the window of 0 is removed. But if something is lost, the ACK is lost, for example, then things could be blocked. And we've seen how to remove that. The slow receiver, the receiver, when it receives, the transmitter, when it receives a window of 0, starts a timer. And after some time, we'll send a probe packet. So that's the universal recipe to remove deadlocks and all bad situations. Some of you might take the courses in distributed systems. You will learn that when you have distributed systems, like we have here, most practical things are impossible if you don't have timers. So it's impossible to know exactly what others are doing and be sure that you know exactly what they're doing, unless you assume that you never lose packets, which is, in our case, not the case, obviously. So the basic thing that TCP does, like we have seen in the stop-and-go protocol as well, is to start a timer. For every packet that is sent, TCP records the time at which it's sent, and there is a timer routine that ideally would, when the timer fires, will detect that this packet is lost. In practice, you optimize to avoid looking at individual times one by one, but intellectually that's what you do. So you start a retransmission timer for every packet transmission time that gives you the date at which this block of data is considered lost if you have not received an acknowledgement for it. Of course, when you receive an acknowledgement, you get rid of the timer. You don't bother about it anymore. And of course, the timer should have the correct value. If the timer is too small, then you will have a stupid system that is always retransmitted packets several times. And too small means if it's smaller, that the time it takes for the destination to ACK it, which is called the round-trip time. So the round-trip time in TCP is the time transmission both ways, propagation both ways, plus the processing time at the receiver, and possibly also the waiting time at the receiver if the receiver has optimization about when to send ACKs, for example. What TCP sources do, they have a routine for estimation of the round-trip time. So they put a filter. Every round-trip time is measured. The round-trip time is when you send a block of data. When an acknowledgement for this block of data comes, you measure the time difference between when it arrives, when you receive the acknowledgement, and when the packet was sent. So you have an estimate of the round-trip time. There are many subtleties in doing that. If you think something was lost, you don't want to measure the round-trip time. So you have raw measurements of the round-trip time, and then you put what is called here a weighted moving average filter. From this raw measurement, you decide about a smooth measurement, which is given by those formulas here. So those formulas have the effect of somehow putting an error bound that accounts for the variability of the round-trip time. I'm showing in black in this figure the value of the round-trip time, and in pink the value of the round-trip time estimate, which is called in TCP RTO. And we see that if the round-trip time is very constant, strictly constant, the estimate will be this value. If there are small fluctuations, it will be larger. If there are sudden fluctuations in one way or the other, this is captured by the error bounds. And hopefully, with this method, the round-trip time is always, RTO, is always larger than the real round-trip time. You can't guarantee it. Of course, you cannot guarantee that after a period of constant round-trip time, all of a sudden there would be a single step here, and the increase is very large. In that case, RTO would be wrong, and then you might retransmit a packet unnecessarily. This is unavoidable, but in most cases, this will be avoided by this estimator. So that's the second element of retransmission. So basic version of TCP would do fast retransmit and timer-based retransmission. We will see that whether there is timer of retransmit, there are implications on congestion control, but that's for later. For the time being, with that, we have a TCP version that works fairly well. When there are streams of packets that are being transferred and isolated losses, they will be detected by fast retransmit, which will typically be faster than with the timer. In particular, if there are periods of time like this where there are large variability, you see that the time to detect here might be several seconds here. So RTO is typically large due to the need to be conservative, and the goal of fast retransmit is to retransmit earlier. When you download a video, for example, and you lose a few packets, if your RTO is very large and if the losses are detected by RTO, that means for perhaps several seconds, the loss will not be repaired. Now, if your playback buffer is a few seconds, you will not see it. If it's a bit smaller, you will see that the video will hang. When does fast retransmit fail? And the majority says C, which is probably true. In particular, one thing that fast retransmit will not be able to detect is the last packet. If you send a burst of data and the last packet is lost, then of course there will be no duplicate acknowledgement after that. So if the last packet is lost, it will take a retransmission timeout to retransmit it, to have it retransmitted. This is called the famous tail loss problem. There are also heuristics to fix that, but we will not discuss them here. Packet reordering, we will discuss now. Well, the goal of fast retransmit is to be able to live with packet reordering. So if there is a stream of packets, we don't react immediately. But if there is packet reordering, that gives the illusion of a loss for a short period of time. But if the packet reordering is large enough, then this will probably be detected by fast retransmit. I say probably because there is another method that has been developed, which is called recent acknowledgement, RAC, which is based on timings. Many of the heuristics are based on counting how many duplicates you receive, whether you receive them. If you receive many duplicates, then you consider there is a loss. But some people here at Google, I believe, made the observation that this is not, in fact, a good symptom, because the reason we might want to not retransmit as soon as we see a gap in the acknowledgements is because we think there might be reordering. Right? So if I come back to this thing here, if we would be sure that the internet never reorders packets, then we could be sure here that we should retransmit. As soon as I receive the ACK for this packet, I should retransmit. Perhaps this is what this system did, because if there is a gap, I receive an ACK for packet 5 and not for packet 3 and 4, that means they are lost, or the ACKs for them were lost also. So that motivates another heuristic, which is called, as I said, recent ACK, which simply keeps an estimate of how much reordering occurs on the path between A and B. So this is useful only for long-lived TCP sessions, typically when you watch a video, for example. Then it's possible to observe the amount of reordering by looking whether you receive ACKs, you receive SACKs when there was no loss, for example. So a TCP that does RAC will monitor some quantity called the reordering window that is usually very small, or even to zero if there is some evidence that on the path you never see any reordering. So there is an algorithm to estimate this. When you open a TCP connection, this value is fairly large, like for example 25% of the round trip time. Then as you have evidence of no reordering, you decrease with similar filters as we have seen before. And then if you receive an acknowledgement for a packet that is after a previously packet plus this margin or due to the reordering window, you decide that you retransmit. I'm showing an example here. Here, packet P3 is sent and lost, and packet P4 was sent, let's say, several milliseconds after packet T3, after P3 at T3. And assume the reordering window estimated by this system is 1 millisecond. Then when we receive an acknowledgement at time A4 for packet P4, with this heuristic, we will say, oh, packet P3 is missing in this acknowledgement. There will be an acknowledgement with a SAC block saying packet P3 is missing. Since packet P3 was sent much before packet P4, it must have been lost, because the only other alternative would have been, because it's not acknowledged now, the only alternative would be that it will come later. But if we believe in our estimate of the ordering window, we think that will not occur. So that is a more aggressive, fast retransmit alternative. It's implemented in Android and other systems developed by Google. Our last additional heuristic is motivated, not last, but last but one, is motivated by denial of service attack. When TCP transfers data, it needs first to open a connection. So when you are a TCP server, when you receive a SYN packet, this triggers opening the connection. And before anything happens, what the server does is to start the connection. Starting the connection means keeping state information. First, there is state, as we saw normally in the operating system, will create a new socket, which is ready for handling the connection. And it will need to remember things like, typically in the first packet of a TCP connection, in the SYN packet, you signal in a header extension what is the maximum size of the packet you can exchange for this data. Remember, TCP has to segment the data, find a good size for the segment, and this size of segment has to suit at least the two ends of the connection. So this is one of the state information that you need to keep here. Now imagine you're a bad guy and you want to attack a server. Then one very cheap attack is to write a script that would send only SYN packets to the server. So you would write a program like we will do in Lab 3, where you start a connection, and that's the only thing you do. Your program will start the connection, drop the rest, and do it again. If in addition you're a really bad guy or a foreign army, then you can have robots that will do it for you, that are infecting other computers or on your own infrastructure. And this will do a very effective denial of service attack on a web server. So that's very, I would not say popular, but fairly frequently used among all the attacks against web server. If you want to bring a service down, you do a denial of service attack by flooding the server with SYN packets that never serve anything. Why is it an attack of the server? Because the server now very quickly will create state information for each of those connections. When it has reached its limit, which is perhaps 100,000 or 1 million connections, then it is saturated. It's unable to accept any other connection. Of course, sooner or later, those connections will time out, but those timeout values are fairly large because, as we will see, there might be things like packet losses for the legitimate connections. So this is illustrating here. Normally what you do, if you're a legitimate user, you send a SYN, the server sends the SYN ACK, and at this point in time, the server keeps state information about you. If you're a malicious user, the rest here never happens. But this guy a normal server, when it receives this SYN, it sends the SYN ACK, and the SYN ACK, if you look at it carefully, it is, you expect it sends a sequence number, and the ACK of this packet is expecting that the sequence number is increased by 1. I mentioned that already last week. When you are a TCP system and you send a packet, you expect an acknowledgement of this packet if this packet contains some data. If you send just an ACK that has 0 data, you don't expect an ACK of your ACK. Otherwise, you would need to keep track of not only the data you've sent, but also the ACKs you've sent. This is not done in TCP, except for the control packets like the SYN and the SYN ACK, where you expect this packet to be ACKed. And to make sure this is consistent with the rates of TCP, we advance the sequence number by 1 in those packets. So it is as if they would be sending 1 byte of information. To make a long story short, this server that has received the SYN sends a SYN ACK, and as a well-behaved server, opens some state for the connection, remembers the MSS, and expects to find a SYN ACK, an ACK of the SYN ACK. If that ACK does not come, the server will resend it, like you do for any TCP packet, using one of the resending heuristics. So here probably there will not be fast retransmit. So if this ACK is lost here, the server will retransmit it when there is a timer. The timer at the beginning of a connection always uses a large value because we don't know what the round trip time is, so the server will wait several seconds. So every single SYN sent to a server keeps the server busy or doing something for a period that lasts for up to several seconds. Now imagine if you send a very large number of that, your server is down. The trick is to offload the server by using cookies. So what are cookies? Well, if you go to a website for shopping, you will see cookies typically. Most websites won't work if you don't have cookies. Why are cookies invented? Well, what is the largest problem if you design a server, if you install a server for your website, for example? What will be the largest problem that you might find?
State.
Keeping state. Identifying users, yes. That will not be the main problem you will have. Storing user data, yes. But all of that you will need to do, but you don't control how many users you will have. La fête des vignerons that happens every 25 years, when they opened the server 25 years ago to sell the tickets, it went down after a few minutes because they did not expect so many requests to come. They had hundreds of thousands of requests within a few tens of minutes, and the server was not able to support that workload. Even if you do flow control for each connection, but if you have a very large number of connections, you need special mechanisms. So of course, if you do a server, you need to have mechanisms to prevent this congestion collapse, but that's very difficult to do. The major thing you want to do when you do a server is make sure your server is as scalable as possible, does as little work as possible. So you have to have lazy servers. Now, most servers need to keep state. For example, if you're shopping, you've started to shop, you've bought 1 bottle of good wine, and then you put it into your basket, then you move around, then you would like that when you come back to the page, your basket is not lost, right? That's very irritating. So the server has to keep state, has to keep a track of what you've done so far. The way servers do it is they delegate the state to you. So they write the state in a small file called a cookie, and they send it to your machine. So that if a server is handling 1 million users, it has 1 million storages to keep the state. Of course, if you need that, you need a bit of security to make sure the user is not forging the state. So we typically use some kind of cryptographic hash so that the server signs the state and sends it to you. And when you want to do something, you send it back to the server. And in fact, it is you who are saying to the server, here is my basket, here's all the things I've done so far. The server verifies that this has the correct hash because the hash uses a secret key that you probably don't know. And if it's a cryptographic hash, it's very hard to forge a collision. Therefore, the server will take your state. So state delegation is the very, very common thing we do in distributed system to offload the work of server, and it's synonym of cookies. The SYN cookie uses exactly that. when a TCP server receives a SYN packet, it will change the behavior of the normal socket. It will say, thank you very much for the SYN packet, but the state that it requires, it will send it back to the source in the form of a cookie. Now, if the source is malicious and it was a SYN flood attack, the rest never comes, so there is some harm done to the server. It has to spend some processing time, but much less than it would do if it had to do the full job. So the server will take the SYN packet, do a little of work, and send it back to you. If the connection never comes back, the server has already forgotten about it. So there is no state kept in the server. So that's a very efficient mitigation attack against the SYN flood. So a SYN flood attack is what is called sometimes an amplification attack. When you do a SYN flood, by sending a single SYN packet, you create a huge amount of work on the server. So the SYN packet is amplifying the work that you had to do. With SYN cookies, which is the mitigation system we have here, we avoid the amplification. So if you want to attack a server, you will need to send huge amounts of traffic to the server, which is still possible, but it's also easier to detect and to counteract by having packet observation in the network itself. So in detail, how does the cookie work? Now, of course, the trick is to send a cookie to a TCP client. One way would be to use a TCP option. We will see how this is done in a second in another optimization. In this one, the smart trick is to reuse the sequence number. When the server sends the SYN ACK, it is also opening the connection in the reverse direction, and it gives what is the initial sequence number. The sequence number is 32 bits. So it will use these 32 bits, in fact, not as a random number, which we typically use, but as a number that encodes the state that it would like to send to you. The state is essentially the maximum packet size, which is encoded in 3 bits, which means that there are only 8 possible maximum packet sizes that are accepted by those kinds of systems, which is fair enough. In reality, the practical ones are even less than 8. It sends a time, also a timestamp, a very coarse timestamp at the granularity of tens of seconds or a minute. So it will make sure that if the cookie comes back days later, then it's considered as invalid. And all of that is signed by sending a hash that is made by using some cryptographic function with a server key. So you take the secret key, the timestamp T that is here, the MSS, also things like the port number and the client IP address and port number of the client, and you hash all of this. And that gives you this thing that is 24 bits. 24 bits mean, if we believe in the cryptography that is used here, if it has not been compromised, it is practically impossible to break it. So the only thing you can do if you want to break it is to do a brute force attack. So you would need to try all possible hashes to find one that corresponds exactly to that. But since there is the server key, the chance that you succeed is 2 to the power minus 24. So it's very unlikely that it will work. Now, what will happen when the server sends that? If you are a legitimate user, your job normally as a TCP is to send an ACK which will contain the number y+1. So the server will see this, decrement by 1. And by decrementing by 1, it will have this value here. So it will know the MSS for this connection. It will also know the time at which, in the local time of the server, it was sent by me. I am the server. And then it can also verify the IP source address and the source port number of this guy here. And if all of this is correct, then it says, yes, this is a valid TCP connection. So only now I will keep state information. Of course, I will not prevent me from being attacked by legitimate TCP users, but those legitimate TCP users will need to do all the stuff of opening a TCP connection. So they do as much work as me. There is no amplification. So we've deleted the amplification aspect of this attack here. If, in contrast, the SYN was bogus, if it was a fake one, then the ACK will never come, or as we said, it's impossible to forge a correct ACK here with the correct hash. So the server will simply receive ACKs that don't match the hash. It will record I am being attacked because there are guys that are sending me things that don't correspond, and it will silently drop them. Now, to meditate on this, a small question for a server that would not implement SYN cookie. So if we contrast what we gain in the server by implementing SYN cookies versus not implementing it, and the correct answer is C, which is the majority that you see on your screen. So if you are, as I mentioned before, if you don't implement SYN-ACK, if this is not sent, then you will try to retransmit this until hopefully you decide that you should not try anymore. So there should be a TCP timeout where you say after trying to retransmit something and you're unable to correct it, you have to reset the TCP connection here. And until that happens, you will keep state information. This is precisely what SYN cookies will avoid. Now, if you do implement SYN cookies, here is another question. And the correct answer is A, the majority. So there is a price to pay for SYN cookies. You don't keep state information for a long period of time, but there's more work to do. You need to do compute a cryptographic hash, which might take a bit more time than simply immediately sending a SYN-ACK and starting a timer. Yes?
There's one SYN cookie per user. What happens if a user, for example, has logged to the server from several devices, one from himself and one from the laptop? The same SYN cookie will be for the whole device.
So if you have several clients going to the same...
Under the same user, yes. The same session, for example.
Well, if you have the same source port number and the same IP address, because the SYN cookie is computed using the source port number and the IP address. So it's the same TCP connection. A TCP connection is identified by the combination of the server port and address and the client port and address. If the combination of those four elements are the same, it's the same TCP connection. So if you do that on your system, you have a problem somewhere. It won't work. If you have the same IP address on two systems, it usually means there is something between the server and the system, which is, normally at EPFL, your smartphone and your laptop don't have the same IP address when you talk to me. But if you do, if they have the same, it's because you have a NAT in between. But a NAT, as we have seen, will make sure there's no collision on the ports. It will change the port numbers such that they're different. Of course, if you don't do that, the system would collapse and NATs would not exist. Question?
If I had the laptop and my desktop, the cookie from my laptop, put it in my browser on my desktop, masqueraded all the traffic coming from my desktop, wouldn't they think I was still on my laptop?
So you want to transfer a cookie from one system to the other.
I don't want to log back in on my desktop and transfer the cookie, just masquerade all.
So a SYN cookie like this one, or a cookie sent by a web server?
So that server gives me a cookie.
Then this cookie has probably your IP address and your port number and perhaps other information. So if you transfer them to another system, you have to make sure they will use exactly the same port number and the same IP address. It's very unlikely that you will use exactly the same port number. Perhaps we can discuss that in a minute at the break. The last optimization we will see now is called TCP fast open, which is an optimization that is trying to break the need to open a connection. And the idea is, if you have repeated connections, so if you do an isolated connection, you go to a website once, this will not help. But if you go repeatedly, if you go to a website with HTTP2 today, normally you will try to have a single connection over which HTTP will try to smartly multiplex all the elements of the page. But if you stop and restart your interaction after some time, you'll need to reopen a new connection. So the idea is very similar to SYN cookies. It is to use a cookie to avoid the SYN and SYN ACK. So if you open multiple connections, the first time you go to the server, if TFO is enabled, you will receive a cookie in the SYN. So the cookie is, like before, sent by the server, and in the SYN ACK, it will send the cookie. Now it's a true cookie, which is much larger, and is not put in the sequence number, but in the TCP options. In the headers, you can put header extension for as large options as you want. So this client will store the cookie. Now the connection, the previous connection is not shown, is dead here. And then when you start a new connection, what you will do is in the SYN packet, so it's not like in SYN cookies. In SYN cookies, the cookie was used in the ACK of the SYN ACK. Now, when you open a new connection, in the SYN packet, you show your cookie. So you show the cookie directly to the server, and then the server will check the signature of the cookie and will now accept to have data in the SYN packet. So normally, when you open a TCP connection, in the SYN packet, there is no data. But here, with this option, you allow to have data in the SYN packet. And the server, if the server is able to verify the cryptographic hash that is given here, it will accept your data, immediately open and fork a socket in the connected mode, and accept the data, so that you are able to start the connection immediately. So this is often deployed by lots of websites. The drawback is it's incompatible with SYN cookies, so those websites are susceptible to SYN flood attacks. So usually what such websites have, they have some software that's trying to guess whether there is a SYN flood attack. As soon as they see an unusually large number of SYN packets coming in, they disable TFO and start SYN cookies instead. Voilà, so this is all for this part. After the break, we will talk of error recovery in general and move on to multicast. So we do a break and resume at 1:15.